All right, outline the 4 processes that make up a Carnot cycle. So let's just do this classically, right? Pressure, volume. All right, the first one is going to be an isothermal expansion. One. Okay. Isothermal expansion, right? Followed by an adiabatic expansion. Notice that the adiabatic expansion has a steeper thing. It drops us to a lower temperature, right? Okay. That is followed by an isothermal compression. Which is then followed by an adiabatic compression. Adiabatic compression. So these guys are isotherms here. And then these are the adiabaticotherms. I don't even know what they're called. There's got to be some name for that, right? Okay. Let's see. Sketch it on a... And you could, obviously you could start here. It doesn't really matter, but this is it, right? Understand that really what's going on here graphically is you've got these isotherms. These are things that are the same temperature. And you use the adiabatic processes to get from one temperature to another. Okay. Now let's see. Why does an isothermal process cause no net change in entropy? Well, here's what it is, right? Is that in an isothermal process, the gas is at the same temperature as the reservoir. And so heat flows into the gas here and flows out of the reservoir. But the heat is the same and the temperature is the same, right? So our delta S is positive some Q over some temperature plus negative some Q over some temperature. Since it's isothermal, the temperatures are the same and the heat is the same, and so that's 0. Okay? Why is an isothermal process hard to pull off in a timely manner? Well, because literally, let's take a look at the compression here. This is the easiest one for me to explain. As you compress a gas, you're doing work on the gas. You must be giving it energy. The temperature must rise, right? But what we're saying here is that we do it so slowly that the temperature doesn't have a chance to rise. The temperature can't rise. So that means that we have to add it. So we have to compress it so slowly that it stays at exactly that temperature. Now, this is impossible. It's impossible to do that, right? But what we could say is that as you approach an infinite amount of time to complete the process, this process approaches being isothermal. And of course, that's where we are, right? So the isothermal processes are really very theoretical. They cannot be done. No one's ever done one, right? Because an infinite amount of time has not yet passed, okay? Now, adiabatic processes happen all the time, or essentially adiabatic, right? All you have to do is do something quickly. Because remember, adiabatic just means Q is 0, okay? No heat flow. And this is why they cause no change in entropy, because change in S is Q over T. Q is 0. So anything divided by 0 divided by any number is still 0, right? So adiabatic processes are 0 entropy because there's no heat flow, right? The change in S is delta Q over T. I don't care what T is. Q is 0. Therefore, that's 0, okay? So adiabatic processes, you can practically pull those off all the time. Isothermal can't really be done. It's sort of like this ideal process, okay?